If anyone can start, okay. That's great. طيب. Today, inshallah, we will discuss the power system model for low frequency oscillation. Low frequency oscillation, or we can say dynamic stability. Time frame here, as you know, a few seconds after the disturbance. This is the time frame. Transient stability, of course, few milliseconds or few cycles after the fault. Or dynamic stability, or what we call low frequency oscillation problem, this would be a few seconds, 5 to 10 seconds after the disturbance. So you allow, in 5 to 10 seconds, you allow the exciter to improve the damping of the stability, or of the system, damping of the system. In transient stability, in few milliseconds, the exciter system will not be able to provide any damping. It is compared to few milliseconds, it's slower than this. So, but 5 to 10 seconds, you allow the exciter to provide a damping signal to improve the system stability. So, dynamic stability, if we mention low frequency oscillation or dynamic stability, we will have the synchronous generator model. In addition to this, we have the exciter model. So we will, our model now is including the synchronous generator and exciter model. If we increase the time to minutes or so, we can have here the governor model and turbine model, mechanical part of the system. Okay, so this is the topic for today, inshallah. And we already provide, or we already discussed the synchronous generator model, and we also discussed the exciter model. So we have in synchronous generator model, we have a second order model. We have the third order model, fourth order model, seventh order model. And for exciter, we can have third order model of the exciter, and we developed it for stabilizing transformer and saturation and all these issues in exciter modeling and so on. But we will limit ourselves here in the exciter round for first order model, as we highlighted in that handout. And we will take the first order model. By the way, first order model for the exciter represented the worst case scenario. And if you consider the stabilizing transformer, this stabilizing transformer will improve the damping, will improve the stability. So for the first order model, we neglect or we remove the stabilizing transformer, so we are on the safe side. And if the system is stable under this modeling of the exciter, but definitely if you increase the modeling of the exciter to include the stabilizing transformer, the picture will be better. Okay. But what is the low frequency oscillation? Why we call it low frequency? What do you think the low frequency that we have here in this problem in dynamic stability? How much of the frequency? Any idea? How much of the frequency that we are targeting here or discussing here? Ayub?
You mentioned it one time from 0 to 3 hertz.
Yes. This is the frequency of the oscillation. This is the frequency of the oscillation. It has nothing to do with the frequency of the system. Frequency of the voltage, frequency of the current is 60 hertz. But these low frequency oscillations are associated with delta and omega, mechanical part of the system. Sometimes we call it electromechanical, sometimes we call it electromechanical oscillation, electromechanical modes of oscillation or electromechanical modes of oscillations. So this is the frequency range that we are targeting now. If you have a disturbance, load change, generator change in reference voltage, in reference power, fault in the system, we may have some oscillations in this order, 0.2 to 3 hertz. And these oscillations, if there is no enough damping in the system, this oscillation may grow up and causes system instability or system separation. And this is usually the case for the interconnected system. When you have two interconnected systems, so the electricity company in the eastern operating area is connected to central operating area. So this is a very long transmission line. Reactance is high. So this is a weak link or weak tie. Power equal to V1, V2 over X sine delta. So X is high, so the power here is limited. So when we have such oscillation, low frequency oscillation due to disturbance, either here or in eastern area or central area or through the transmission lines, we may have such oscillations. If there is no enough damping in the system to damp out this oscillation as such, in this case, we may go and isolate the operating areas. So we have system sectionalization or system separation. So, and this is very, very crucial problem. And it is not an easy to have an interconnected system and you switch on off, you connect them as such. It is not an easy issue. And you may, with this separation, you may create instability in this area and also instability in this area. For example, if you have a huge power transferred here, B12, if you disconnect, so we have here generation is higher than the demand. And here you have the demand is higher than the generation. If you separate this. So in this case, you may lose, you may go to blackout here and blackout here. Or at least you have to to manage. You have to do some under frequency load shedding, and you have to have countermeasures for this situation. So it is not an easy to separate the interconnected systems. So don't underestimate the problem. When somebody say, 0.2 to 3 hertz, this is not a big issue. This is a big issue. Don't underestimate the problem. In order to address this problem, we need at the beginning to we have so many questions. Hussein, please.
Yes, Doctor. Now, what will take the action and cause this separation? Is it a controller or?
Yes, of course. طبعا protection, of course. And when we say separation, we have a protection. Okay. يعني separation يبقى في protection system يعني. الكنترولر we have controller we have here controller, and this controller is bar system stabilizer, and we have here also bar system stabilizer or controllers here and there. But if there is no enough damping, if these controllers are not giving enough damping for this oscillation, so this oscillation will start going up and down and increases with time. So after 2, 3, 4 seconds, you can have this power is not in this way, but it's going this way and this going this way. So you have what we call the power slip. We call it power slip. And the generator, if you have a generator, assume this is a generator. Or assume this is a load and this is a generator. This is the power comes from here to here. This is the load and this is a generator. Now, if you start having the oscillation and this generator with this power is going up, increases and decreases, you may have it negative, means that this power is going this way. So this generator becomes a motor. So you have what we call the bull slip. So this is طبعا, of course, in the protection system, you have to protect your generator and you have to isolate it. So this is of course, you have out of step relay. So they call it out of step relay.
Yes.
Out of step relay. Okay.
Yes.
Okay. طيب عمر Salman.
Yes, Doctor. I want to ask, how do we get to say that it is low frequency oscillation is occurring? If you're not in the industry, let's say we are, as I am inside my room, and maybe a low frequency oscillation has occurred somewhere. Is it possible that does it reflect anything in the customer's end?
And the customer?
Yes, in the consumer's end, does it show? Can I, as a consumer, and who has technical understanding of the power system, can I observe a low frequency oscillation right in my building?
Okay, actually, low frequency oscillation, when you have this power, for example, between these two bars, you will see the power is oscillating as such. So the power is increasing, decreasing, increasing, decreasing, and so on. This will also reflect the voltage. If the system becomes unstable, the voltage will be oscillating as such. So the voltage will not be stable also. But if you are the end consumer, in this case you will sense the problem. But of course we will not. But this is if the system becomes unstable. Unstable معناها إنه you beyond now the protection حتى scheme. And the protection will do the separation here in order to improve the system stability. At least we sectionalize the system in order to isolate the problem. So we can keep part of the system alive. This is the way it is done. So as a consumer, you will not reach to this. This means that the system is unstable. معناها انه there is no protection system, there is no controller, your system is still running, which is not the case in real life. As I mentioned, when we have this oscillation, big oscillation here for the power and increases with time, then the protection system will take an action. And the controllers are not able to preserve the power or to damp this oscillation, but then the protection scheme will take place. Is it clear?
Yes, thank you, Doctor. Yes.
Okay. In order to address this problem, lower your hand if you don't have any other question. Okay. So in order to handle this question or to address it, as you can see here, we have a small oscillation and the long time. So we can linearize the model. We can linearize the system. We can linearize it. And we can work on the linearized model. For transient stability, you cannot do this. We have very abrupt change, very short time, the system is highly nonlinear, so we cannot linearize in transient stability. But in dynamic stability, or specifically for low frequency oscillation, we can linearize the model. If we linearize the model, then we need to have the initial condition in order to linearize the model under the operating point or around the operating point. So we can linearize around an operating point. So this operating point will be specified by the initial condition, initial angle, initial voltage, initial current, initial power, all these quantities, the initial condition calculated. So we will see how to calculate the initial conditions. When I say voltage, I mean the two components, direct X and the quadrature X, VD and VQ, ID and IQ, angle, the root power angle, real power, reactive power output of the generator, initially, how much, and so on. So this is the initial condition calculation. We have two ways to calculate the initial condition. If you are given the electric power output of the generator and the reactive power at steady state and the terminal voltage magnitude, if you have such quantities, you can find all the initial conditions that we need to linearize the model. The initial conditions, as I mentioned, VD, VQ, ID, IQ, power angle, and so on. So if you are given the electrical power, reactive power, and the terminal voltage of the machine, we can use this piece of information and we can have all the quantities required here. And this is usually the case. Usually when you solve the load flow problem, you have the terminal voltage from the load flow, and you have a real power and reactive power output of the generator. So these are some local measurements you can have, and then you can find all the other quantities that we need for linearization. Another case, if you are given an electrical power, a terminal voltage, and infinite bus voltage. This case is rarely used. No terminal or infinite bus voltage is not a local measurement. So you have here some local measurements here, but this is not local measurement. So that means you need some communication. And also, what is the infinite bus? And should I measure where? The infinite bus is actually an assumption. So this case is rarely used. So we will focus on this case. So we can find all the initial conditions, VD, VQ, ID, IQ, and angle, and so on, if you are given such quantities. So we will develop the linearized model. And linearized model constants, we have famous constants in the linearized model of synchronous machine. This is K1 up to K6. We will derive what is the relation between these constants and the initial values. Now, what we need to linearize? Why do we need to linearize the model? And actually, we need to improve the system damping, and the ultimate objective of our discussion here is to develop a controller in order to improve the system damping to this problem, low frequency oscillation. So we will do linearization, and then we will design a power system stabilizer in order to improve the damping. So this is the ultimate objective, but this is maybe covered in the next class. So we will develop first the linearized model, and then we will see how to design the controller later on. Any question? Okay. We started thinking about this problem in 1960 in the order of few cycles per minute. This is the low frequency oscillation. And a few cycles per minute, معناها انه low frequency. عندنا 60 hertz is 60 cycles per second. So this is few cycles per minute. Have been observed when large power systems are interconnected by relatively weak tie. Weak tie means what? What do you mean by weak tie?
High reactance.
The X tie is high. So this is the weak tie.
Yes.
So we have, limited power transfer. Yes, you are right. So if you still remember the natural damping, when we have the mechanical part of the system, the swing equation, and we linearize the swing equation, and we develop the omega n natural frequency of oscillation. Natural frequency of oscillation or low frequency oscillation. If you still remember, what is the order of omega n that we calculated in examples or in problems before? What do you think omega n would be? In which order? Yeah?
Three, 7, 3, 4, 2, 3, 3, 7 something.
Okay. So in the order of plus minus, طبعا there is no minus, يعني 10 plus minus يعني epsilon or whatever. And it could range from omega n, could range from 3 radian to, for example, 18 radian per second. So omega n equal to 2 by f. This is the frequency of oscillation. So frequency of oscillation equal to 3 over 6 approximately. So 0.5 hertz. Frequency of omega n equal to 18. Natural frequency of oscillation, so 18 over 6. So it becomes 3 hertz. But this is the range, and you can go with low frequency of oscillation than 3 hertz or 3 radian per second. Okay, these oscillations may sustain and grow to cause system separation if no adequate damping is available. With more experience accumulated from interconnected electric power systems operation, power system engineers are now convinced that the low frequency oscillations are due to the lack of damping of electrical mode of the interconnected system. and the desired additional damping can be provided by supplementary excitation controller called power system stabilizer. And the power system stabilizer will be installed in the excitation system. If you still remember, when we discussed the exciter system, we have here a summing point where this is the terminal voltage and this is the reference voltage. And we have here other signal. If you still remember this other signal, احنا قلنا ان الother signals ديت هي power system stabilizer. So you may have here a controller that gives the controller input or controller output will come here in the excitation system. This is the automatic voltage regulator and so on. So this is EFD. So this controller power system stabilizer will affect the voltage, the field voltage, and in turn this will if it is designed well, it will improve the system damping. Of course, if you still remember, if you change with this power system stabilizer, if you have here a control signal, this will affect the EFD, and EFD, if you still remember, will affect what? EFD will affect what? If you still remember the machine model, this is the exciter model. EFD will affect what? Which state in the machine? In the third order model of the machine. الناس بتتابع ولا؟
The internal voltage.
Internal voltage, EQ prime. And if you change the EQ prime, then you will change the, of course, the mechanical, the electrical power or the electrical torque, TE. And this will affect the VD and the VQ, and this will affect also if this is the case, you will affect delta and omega. So if you have such a signal here, this will affect all the states of the system. The system is not, decoupled. The system is, you have coupling among the states, and this is usually the case. So if you adjust the field voltage, this will improve the response of delta and omega. Yeah. During low frequency oscillations, the current induced in the damper winding is negligibly small. Of course, here we are talking about very long time. Very long time مش معناها hours, very long time معناها 2 seconds مثلا. لا, damping winding, if you have the damping winding, the transient or time constant of the damper winding TD prime or TDO prime, if you go back to this equivalent circuit, this is VD, and you have here RA, leakage of the armature, and reactance or mutual inductance here, XF and RF, and XD, D capital, and RD capital, damper winding here. If you calculate TDO prime, which is and we did already, we developed the expression for calculation of this. We don't need to, or you don't need to memorize these expressions, but if you want to calculate the time constant here for the damper winding, time constant equal to the equivalent inductance over the resistance here, L over R. This is the time constant. So L over R. So what is L here? L here equal to or X over omega or whatever. And you can express it X over omega, which is L, and RD capital. What do we have here? We have XD capital plus you have XF and XMD are in parallel. So XMD over XF plus XMD. So try to, and I am emphasizing on, don't memorize. No need to memorize them, but you can derive all these expressions in as we have here. So TDO prime is very, very short. You can have it 0.0 مثلا 0.5 second. So in just 5 milliseconds, طبعا assuming انه if you have the time constant equal to this, maybe after 4 time constant, after 4t, you reach the steady state. So that means you steady state here, these are short circuited. The steady state بتاعها in voltage 0, current 0. So it doesn't play any role. After 4 time constant, and after about 20 milliseconds, the effect of the Dunbar winding will disappear. So this is why in dynamic stability or in low frequency oscillation, we are considering the Dunbar. We are not considering the Dunbar winding here. Okay, so as for the D and the Q armature winding of a synchronous machine, their nature of frequency, طبعا these are armature winding, يعني بنتكلم عن electrical part of the machine. The nature of frequency of the electrical part of the machine is very high, and also the dynamics here will not be considered for the armature winding. So what we have the mechanical part of the machine, internal voltage, and the field voltage. So we have delta, omega, EQ prime, and EFD. So these are the states in the low frequency oscillation. Of course, you can use third order model of the machine +1 for the exciter, or you can use also the 2 axes of the machine, EQ prime and the ED prime, plus also 1 of the exciter, and you can. But usually we will consider only the fourth order model of the system, 3 for the machine and 1 for the exciter. Okay. What is left in the field winding? That must be described by a differential equation, EFD dot. Field winding, you have to take into consideration the EFD because it's low eigenmode frequency, and also, and the most importantly, the supplementary excitation control is applied through the excitation system. So we have to model the excitation system. So finally, the torque differential equation of the synchronous machine must be included in the model. Of course, finally, the torque differential equation of the synchronous machine must be included in the yes. Okay, so let me remind you with the model that we will consider in this study. We have the fourth order model, 3 of the synchronous machine and 1 of the exciter. And you have omega dot 1 over m equal to 2h, as we pointed out earlier. Mechanical power, which is considered the constant, and comes from the steady state operating point. Electrical, which is VDID plus VQIQ, minus T damping, if you have any damping coefficient. So damping of D times delta omega, which is omega minus 1. Omega here is considered embryonic. So it is around 1. At steady state, omega equal to 1. Delta dot equal to omega B times the base speed, which is 377, multiplied by omega embryonic minus 1. One is the omega at steady state embryonic. So this one is not, one here is the omega steady state embryonic. So which is the synchronous speed, 1 embryonic. And this is the base value, which is 377. 460 hertz. And this is 460 hertz. For 50 hertz, it becomes 340. EQ prime dot, this is the third state equation. 1 over TDO prime. And the TDO prime also, you can have it from the TDO prime we are talking about. So this is RA, and this is the, and we neglect the Dunbar winding here. And this is a transient, this is a pair only in sub-transient period. You have here XF, RF, XMD, X leakage, RA. So you can have a TDO prime. This is the time constant of the field winding. Time constant here is 1 over omega B, 377, multiplied by RF, field resistance, multiplied by the equivalent reactance in the field winding. So in the field winding, if this is open circuit, and we mentioned in the O here, refers to the stator winding or open circuit. So this is open, so the equivalent reactance here is XF plus XMD. So this is TDO prime. EFD, EQ prime, XD minus XD prime, and these are the parameters of the machine, so you have it. And multiplied by the direct X current, here ID. And the fourth state, which is EFD dot of the exciter, 1 over the automatic voltage regulator time constant TA, automatic voltage regulator gain, KA, V reference minus terminal voltage, plus if you have UBSS. If you don't have UBSS, this becomes 0. If you don't have a stabilizer, minus EFD. So these are the states. This is the nonlinear equations. Nonlinear equation, and we have here TE equal to VD, ID, VQ, IQ. So you have some multiplication among the variables that you have. So this is the nonlinear differential equations. In addition to this nonlinear differential equations, we have some algebraic equation with the model, as we mentioned earlier. One of the algebraic equation is TE equal to VD, ID, VQ, IQ. TD equal to D times omega minus 1. VD equal to XQ, IQ. And VQ equal to EQ prime minus XD prime ID. So this is the nonlinear differential equations, and this is the algebraic equations. In principle, if you are given the initial condition for this system, if you know the initial value of TE VD, ID, VQ, IQ, EFD initial value, EQ the initial value, delta initial value, the omega initial value. How much is the initial value of the omega? How much is the initial value of the omega? What do you think? Initial value of the speed.
It is 1.
It is 1 embryonic, yes. And omega initially is 1. So omega node equal to 1. Of course, you can get delta 0 if you know, طبعا, as we mentioned earlier, we have 2 cases to find the initial conditions. If you have the initial conditions, if you have all the initial values of delta 0, for example, you can solve, if you have any disturbance here, you can solve the system and you can find whether the system is stable or not. For example, if you have 10% step of mechanical power, can you simulate the system? Yes, we can simulate the system. If you have مثلا this 10% step of the mechanical power مثلا at t equal to 1 second. So if you calculate the initial conditions of the system, there is no disturbance up to 1 second. So delta will be constant, no change. This is delta 0. If you have step input here 10%, the B mechanical was 1 per unit, for example, at t equal to 1, it becomes 1.1 per unit. So you can go to this, differential equations and solve for t equal to 1 second. Then you increase the B mechanical. You put it instead of 1, you put it 1.1. Maybe this is for 2 seconds, for 3 seconds, and then it comes back to 1. You can also do step change in V reference. You can allow that 5% of the V reference up or down, and this is usually the case. If you are running the machine, you need to increase the mechanical power or the electrical power output to increase the mechanical power, or you need to adjust the voltage so you can play with the reference voltage. So you can easily solve these differential equations. If you have the initial condition, you can solve with any disturbance in V mechanical or V reference. And this is, of course, we did it before in transient stability. When we have only this, we can increase this as stable input. Okay, so let us start with the initial condition. First case, first step is to validate the generalized model, is to find the initial condition of the system, and this is the typical system that we will consider here. Single machine infinite bus system. This is single machine infinite bus system, and to generalize the problem, we will assume that we have a local load here, and this is the admittance of the local load, conductance and susceptance, and you have a transmission line with an impedance R plus JX, terminal voltage, infinite bus voltage, and you have here current I, which is ID plus IQ, ID plus JIQ, and you have here, of course, BE and QE. Okay, so electrical power and electrical reactive power output of the machine. So let us consider this system at the time being. Later, we can see the multi-machine system if time allows. So what we will have here, this is the local load. If there is no local load, the admittance of the load equal to 0. If there is no local load, so G equal to 0, B equal to 0. So we will develop how to calculate the initial considering this load. If there is no load, you can easily handle it. You can just set G equal to 0 and B equal to 0. Okay, so this is the phasor diagram. You have here This is the infinite bus voltage. This is V infinity, infinite bus voltage. And you measure, of course, delta from the internal voltage to the infinite bus voltage, which is your reference. This is the terminal voltage. This is the current. You can have here the phase angle phi between the terminal voltage and the current. And this is the D axis, and this is the Q axis. EQ prime will be in the Q axis. Of course, you can have VD, and you can have VQ component. You can have ID and IQ component, V infinity D or V0D and V0Q components of all these voltage and the current. Okay, let VT equal to the VD plus JVQ, that's usually the case. I equal to ID plus JIQ. The torque angle delta is defined as shown in phasor diagram, defined here between EQ prime and V infinity. And V infinity also has two components, V infinity D and V infinity Q, which of course you can, V infinity Q, this is equal to V infinity cosine delta, and V infinity D equal to V infinity sine delta. So this is V infinity D, and this is V infinity Q. Based on this, and delta is the angle between this and that. If you have any question, don't hesitate to ask. And don't skip anything unclear. Okay, so Hussein.
Yes, Doctor. In the previous in this slide, we usually have the infinity as a reference with zero angle. But now I see there is an angle between the V infinity and the D axis.
Yes. Yes, there is a okay. Here, when you have machine, this will go to for this machine. For this machine, you have Dx and the Qx, right? V infinity, you can, if you still remember, the Dx or Qx are related to what for that machine? Dx is what? The axis of the field winding, right? So this is the field winding, X. Am I right, Hussein? You still remember this?
Yes, Doctor. Yes. Yes.
This is the direct axis is related to the machine here. Direct axis of the flux or of the bolts here of the field winding, and this is the quadrature axis which is perpendicular to it. V infinity, you can consider that in the V infinity is your reference. You can say, no, this is our reference. But this reference has nothing to do with the D and the Q axis of the machine. Am I right?
Yes. Yes.
So you can assume that in the V infinity, or we consider V infinity as our reference with angle 0. But actually, this angle, if we have the reference here, and if we project all these vectors on this, and you have here, this is V infinity. If you consider this as your reference, and this is the perpendicular to this, so you can have an EQ prime even. You can have projection of EQ prime on the that reference and the EQ prime on that reference. But here, the EQ prime on the quadrature axis. The current, voltage, You can have them a component here and a component here. Okay?
Yes.
But you can relate all the quantities in D and the QX of the machine, which is our case here, or you can represent all the quantities with respect to that reference. But in this case, you have to, this VT now is not VDIQ. Now, VT here is not VQ. Am I right? If we consider this as our reference.
Yes.
فما الدايركت اكس والكوادرشال اكس of the machine. So we need to stick with the D and the Q axis of the machine. So we can come here and say V infinity has an angle, okay, as an angle delta with respect to the quadrature axis. So this V infinity has angle delta with respect to quadrature axis. So we can have V infinity projection here and the projection of V infinity here. So we consider now the direct and the quadrature axis of the machine, not on the of the system.
Yes.
I
Clear.
hope. Okay.
Yes. Clear.
Okay, great. So this problem of the axis and or references considering this will be very clear, and if we have two machines on three machines. If you have this system, so this machine has DQ, and this machine has DQ also, and this machine has D3 and Q3. Each machine has its own direct and quadrature axis. Am I clear?
Yes.
In that case, you can either create a fictitious machine and relate others to it, or if you have an infinite bus, you consider it as your reference, and then in this case, ID and IQ here for this machine, you have to project them here on the system reference. Okay, so you have to rotate ID and IQ. You have to adjust ID and IQ with the new reference here. For single machine infinite bus, we will consider the direct axis and the quadrature axis of the machine, and in this case, we need to project V infinity to those direct axis and the quadrature axis. Okay, any other question? Okay. If you go to the system here, we can write, of course, IT, or I here of the output of the machine. This is the current. We can write it as I1 plus I2, and I2 equal to what? This is the admittance, and the voltage here is known. So VT times YL. So this is the current here. Voltage times the admittance. And the I1, we can write it VT minus V infinity over impedance Z. So I equal to I1 plus I2. And we can start, analyzing this and see how can we get the initial conditions here. So we can write this I equal to YL, or the admittance. We will drop L here just for the convenience. So I equal to Y times VT plus VT minus V infinity over the impedance. So we can have ZI equal to, this will be multiplied here, and you have here VT, so VT multiplied by 1 plus ZY and minus here the infinity. And you can, of course, substitute. You can substitute on Z equal to R plus GX, and I equal to I plus ID plus GIQ, R plus Gx, G plus Jb, Vd plus Jvq, V infinity D plus V infinity Q. And you can write this, and you can have the real parts equal to each other, and the imaginary part, you can have two equations from this. Now what we need is to simplify the analysis later. So we will develop some constants here. We will develop some constants based on this equation in order to simplify the analysis later on. So 1 plus G Zy equal to C1 plus C2. And of course you can get C1 and how much C2. If you substitute on Zy, Z equal to R plus Gx and Y equal to G plus Jb. And you can have the real part and the imaginary part. C1 is C2. So this is C1, and this is the second constant, which is equal to Rb plus Xg. So this is the two constants that we have here. And also we can go forward and replace Vt and V and Id, V infinity, and so on. You can have this equation. This is very simple. You just need to replace I here by Id plus Jiq. Vt, these are the constants here, C1 plus Jc2 here, and the V infinity D and V infinity Q, and this is defined earlier. So you can end up with two equations as such. And this is this represents the real parts, and this represents the imaginary parts of the system. Is it clear? Is it clear, this equation?
I think example is very clear.
I couldn't hear you, Sulaiman. It's clear at the end, yes or no?
I say it's not very clear yet to me, but when we take an example, a numerical example, maybe it will be very clear.
No need for a numerical example. And I hear here, this is R plus Gx and multiplied by Id plus Jiq. This is equal to 1 plus Zy equal C1 plus C2. C1 plus J, C2. And Vt is multiplied Vd plus Jvq. And minus V infinity, which is V infinity D plus Jv infinity Q. So you can have the real parts together and the imaginary parts together. So you have Rid here, and you have minus Xiq. Okay, so this is exactly what we have here. Rid minus Xiq, and you can continue. You can continue separating this real part and the imaginary part. Okay, so this is an important equation. The initial conditions are calculated in the following two cases. Case number one, if you have BQ and the terminal voltage, and this is usually the case, we will concentrate, maybe we will focus only on this one. And the other case, if you have V terminal and V infinity. Subscript 0 is to identify the initial values. The calculation of the initial conditions in both cases are as follows. Let us take the first case, where you are given the electrical power, reactive power, real power, reactive power, and terminal voltage. How to, from this is the characterization of the operating condition. This is the operating condition. And this is the operating conditions. This is the operating. Based on this given values, what we need to find, ID, IQ, VD, VQ, V infinity, and delta, and also EQ prime and EFD. All these quantities we need to have. voltage and the current V infinity, we need to find out how much will V infinity, delta, angle, EQ prime, and EFD. So this is the initial conditions. Okay, let us start with those quantities and see how to proceed to find all these quantities. From B and E, and the terminal voltage also is known, can be calculated as such. You have a BE equal to, or BE plus JQE equal to VT I conjugate. So you can have, as we mentioned earlier, in the BE equal to VDID plus VQIQ, and the QE equal to VQID, imaginary part here, minus VDIQ. So BE is known, given. The Q also is known. So at least we have here 2 equations and 4 unknowns. So we need to develop other equations. The VD equal to XQIQ. And this is, of course, known from the algebraic equation of the model. And also, we have VQ equal to EQ prime minus XD prime ID. One XD prime is parameter, so it is given. XQ is given. So how many variables in these 4 equations? We have 4 equations now. How many variables do we need to find out here? Any answer? Any answer? How many variables do we have?
5.
5. VDID, VQIQ, and also EQ prime. So we need to develop another equation. VT equal to VD square plus VQ square. So terminal voltage is known, is given here. So this is also known. So what you have here, you have 5 equations in 5 unknowns. So we can start substituting, manipulating VD, express it in terms of this, and VQ, replace it, and so on. So you can end up with, definitely you can solve. In principle, you can solve these 5 equations and 5 unknowns. These equations can be solved for VD, VQ, ID, IQ, and EQ prime simultaneously. Eliminate ID from equation 1 and 2. We have this equation. We can obtain this equation. In this equation, you have VD, VQ, and IQ. Solving IQ and VQ respectively from 3 and 5, and substituting the results into equation number 6. And as I mentioned, you have some manipulation with these equations in order to reduce it to one equation, one unknown, and then you can solve. So after this, we can have such equation, which is, we still have here, this is known, this is known, we need this, we need this, which is this same, and this is the equation of only one unknown that we have here. The QE is known, the XQ is known. So all the quantities are known except VD. So this equation can be solved now. You have all the quantities except VD. You can solve for VD. Once you get the VD, then we can go back and solve. So this is VD. VD equal to power, which is known. VT is known. BE square QE VT square over XQ square under the square root. So in this case, you can have VD. If you have a VD and you have a terminal voltage, and you know that the terminal voltage equal to square root of VD square plus VQ square, so you can get the XQ. and from XQ, and then you can handle this simple problem. So VQ can be given, VD equal to XQ IQ, so IQ can be calculated, VD over XQ. You have the power equal to VD ID, VQ IQ, all the quantities are known except ID, so we can calculate the ID. And we can calculate EQ prime, which is VQ plus XD prime ID. So this is the algebraic equation, so we can have an EQ prime. So you can solve for all the quantities of the terminal voltage and the current DQ axis and DQ prime. So what we need is V infinity. We still have EFD. We need an EFD list. Still you have EFD. We need to find V infinity, and we need to find the angle. So we still have these three variables. The initial values of V infinity delta can be determined from the matrix equation that we developed here. For this matrix equation, if you still remember, you have this now. ID is known, IQ is known. These are constants. It is known, depends on the admittance and the impedance. The VD is known, the VQ is known. So you can have V infinity and delta. So you have only two parameters in these two equations. So you can have a V infinity and delta. So you can easily have it.
Doctor?
Yes.
The matrix equation, that matrix equation, the dimensionally, I think the equation, I mean, they are not the same. I think the,
What?
yes.
What do you mean?
Dimensionally.
How? How now?
This is the right hand side, I mean, voltage, left hand side voltage. Then this particular one, the one at the center, the times at the center. C1 and C2 to C1 and C2, they are not, they are impedance. They are impedance as well.
No, they are dimensionless.
Okay.
C1 with C2 comes from Z times Y. Z times Y is dimensionless.
Yes, doctor.
Okay, so these are voltages at the end. This is voltage, impedance times the current, and this is dimensionless, so we have voltage here, and this is voltage also. So it is there, Omar.
Yes, thank you, doctor.
So you can solve for all these quantities, and V infinity from the first equation, if you multiply this R times ID, X, Q, and so on, and you combine them in one side, and V infinity sine delta, or this is the one equation. C1 is known, VD is known, VQ, ID, IQ, all these quantities are known. So you have V infinity D or V infinity sine delta is known. V infinity cosine delta also is known. So either you can divide or you can have tan delta. Divide these two equations together, so you have tan delta equal to this over this. So you can get delta, and then you can substitute in one of the equations here to get V infinity. So you can have a V infinity. Okay. So the remaining is the remaining is EFD. Remaining is EFD. EFD, if you go back to these equations or the modeling of the system, you can have EFD. When we say initial condition or a steady state operating point, these derivatives equal what? These derivatives equal what? At steady state.
Zero.
Zero طبعا. Zero طبعا. This is at steady state. So the EQ prime dot equal to zero. The EQ prime dot equal to 0. Now EQ prime has a value and we already calculated it. So if this is 0, so EFD equal to EQ prime plus XT prime, which is parameter of the machine, and the ID also calculated. So you can calculate the EFD directly. If you have the EQ prime and you have the ID at the initial, so you can have the EFD, and we can add it here, given that in EFD we can write here in the EFD equal to EQ prime plus XD minus XD prime times ID. So if you have an EQ prime there and ID, so you can get the EFD at the initial value of the EFD. So you have the complete values of the initial conditions here. This is the second case, which I don't want to stress on it. Time is not only the time is over, but we have now time is limited a little bit. But you have VE and terminal voltage and V infinity are given. We can define all these angles, beta between VT and EQ prime, and phase angle between voltage and current, delta angle, which is between V infinity and EQ prime, and gamma, which is between VT and V0. So all these angles can be defined. Alpha, the angle of the impedance, X over R. And then you can proceed based on this, based on this phasor diagram. You have this angle is 90. So I don't want to, time is over. Let us stop here and there will be a homework will be uploaded tonight, inshallah. This homework will ask you to develop hand calculation of the initial conditions, and you can develop a MATLAB program to calculate the initial conditions, these initial conditions, if you are given V, EQ, and VT. So you can have directly these equations. You start with these equations and others. You can find the initial condition. And I will ask you also to do some kind of time domain simulation. You have the differential equations of the nonlinear system, and you have the initial condition, and you have the algebraic equation, and then you can simulate if you have a disturbance in the mechanical power or the reference voltage. So we would like to prepare ourselves when we design a controller. We will see whether the system response will be improved or not. So let us stop here and continue next class. If you have any question, please ask, and otherwise you can leave. So we have